We are interested in showing the integration rule that the integral of dx over the square root of 1 minus x squared, did I say square root? I meant square root, equals arcsine of x plus c, and we want to generalize it to having a constant up front. Alright, so to do this, we're going to use substitution u equals x over a and algebra to derive the generalized form. Okay, so for this, I'm going to start off with dx over a squared minus x squared square rooted, and we're going to use u equals x over a. So one of the things we want here is we want x squared. So to get that, we'll square both sides of u. So u equals x squared over a squared. Seems reasonable. And we also want dx, so we're going to take the derivative of both of these. So du, which is a variable, so it goes to du, becomes dx, and then a is a constant, so we just have a on the bottom. And rearranging this, we have a du equals dx. All right, so now let's tackle some of this. So we can say that this integral right here is the same as dx over, I'm going to say a over a, but because this is the same as multiplying by 1, and you can always multiply by 1 in life, and times square root of a squared minus x squared. This is part of the algebra, and the a on the bottom, that's supposed to be an a, not a 2. Instead of calling it a, we're going to call it a squared over square root. Now, true, we lose a little bit of information there in case it's negative, but we're not going to worry about that in this case right now. So this is the same. We haven't changed anything. This is totally fine. Now I'm going to distribute this this a squared under the radical, because this is a radical, that's a radical. We can now combine them. This is now going to be equal to integral dx a times the square root. This is going to be a squared over a squared minus x squared over a squared. Rewriting this one more time, well, at least one more time, hopefully just one more time. Actually, I'm going to put in this, we know that dx is a du, so I'll put that in right now. It's a terrible a du, and then we're going to divide by a square root. A squared over a squared is 1, x squared over a squared is x over a squared. We then get a good canceling color. The a's cancel. We have integral 1 over, and then we know that x over a is u squared du. And so this is of this form up here. So we can then write this equals arcsine of u plus c. And we know that u is arcsine of x over a plus c. So we started with this, and we showed it equals that, which was our whole goal from the beginning. So we used the substitution u equals x over a to prove the generalized form. So this is how we did it using this substitution. So now we're going to do the same thing, but we're going to now use the substitution au equals x. So if you look back up here, we used u equals x over a. Now we basically just multiply both sides by a, algebra, x equals ua. So this is the way I normally do it, and pretty much the way that I've always seen it done. So this is going to be the more common way of approaching this. So we have an integral, let's make sure I get this right, dx over a squared minus x squared square rooted. And there are 3 basically formats which kind of trip your spider senses, make your spider senses tingle. You should recognize. Whenever you see a square root with the difference of 2 squares here, and the negative sign is with the x, you are going to want to do x equals a, and here they just do u, but I'm going to do this as sine of u. And I think you'll see why. It's the same process. It's just going at it slightly different. And as a sidebar, if you have x squared minus a squared where the sign is not with the x, then you would say that x equals a secant of u. And if you have something where it's 1 over x squared plus a squared, you say x equals a tangent of u. And this is kind of start to get the algebra rolling. You plug it in and just kind of see where it goes. You do about a dozen of these and you're like, oh, okay, I see where it's going. This is kind of background. All right, so we're going to do the x equals a sine of u. It's going to be a little bit different from the problem we're solving, but exact same concept. And you'll see where it goes. So with these trigonometric, inverse trigonometric integrals, we're always going to want to find the dx. So the derivative of x is dx, and we're going to have a cosine of u. We're also going to want x squared, which is going to be a squared sine squared of u. And then one other thing I usually solve for as well is I solve for u. So solving for u here, rearranging this, we get u equals arcsine of x over a. And that's just algebra. So these are the four things you're pretty much going to solve every single time when you're doing inverse trigonometric. So now we're going to take this and start plugging things in. So dx is going to be a cosine of u. A squared, well, that's just a squared, so we're going to go with that. Leave it as such. A squared minus x squared. X squared is a squared sine squared of u. Oops, sorry, that's a 2. A squared sine squared. It's also supposed to be another radical there. U. Extend it a little bit. I know that's cheating, but I'm going to do it anyway. Let's see, dx. Oh, I forgot a du here. Chain rule. Du. So now what we can do for this is we pull out the a squared from under the radical. So we have a cosine of u du all over a squared 1 minus sine squared of u. Now this, we can use the Pythagorean theorem here. So we have sine of x squared plus cosine squared of x equals 1. Rearranging this, 1 minus sine squared of x, and I just use x here, but you can use any variable, is going to be cosine squared of x. So this right here, under the radical, which I forgot, this is also supposed to be under the radical, but the square root of a squared is just going to be a. So we have this, a cosine of u du all over, and then there's going to be an a down here. 1 minus sine squared of u is going to be cosine squared of u. Cosine squared of u, but that's still under the radical. Hopefully I didn't lose you yet. The a's cancel. This cosine squared of u square rooted is then just going to be cosine of u. And this is going to give us, that's supposed to cancel. There we go. Integral cosine of u over cosine of u du. Cancel, cancel. This is integral du, which is just going to be u. It's like 1. The integral of 1 is going to be just whatever your variable is. In this case, u. And it'll be u plus c. And now, since I said that x equals a sine of u, we can then plug back in for, since we solve for u up here, we can then plug in for what our value is of u, and we get u plus c, which is our answer, is going to be the arcsine of x over 2 plus, or x over a. My terrible handwriting, my unique handwriting is throwing me off. So we went from the beginning part, which was integral dx of a squared minus x squared is going to be equal to arcsine of x over a plus c. And that was what we wanted to do to prove the generalized form. So I did it a little bit differently than they told us to, because instead of using u, instead of saying x equals AU, I said x equals a sine of u. And that's because whenever you see this form, a squared minus x squared, you can use this trick. If you see x squared minus a squared, square rooted, and the signs with the a, then you say that x equals a secant of u. And if you have an x squared plus a squared, then you can say x equals tangent of u, and you have a similar process that goes through this. All right, and then the third part, all the substitutions are equivalent. They are. It is worth noting that we can use substitution of the form x equals u equals f of x or x equals g of u. So this is what I did. X equals g of u, because I used a function. Or even gu equals fx, as long as we understand the relationship between du and dx. Yes, you need to understand the relationships. Which of the substitutions above do you prefer, and why? So my preferred substitution is, I guess in this case, it would be the x equals g of u. And the reason is just because I have more practice. It's probably not, you could say it's simpler, more efficient, more streamlined, easier to conceptualize. In reality, though, the reason I prefer this is because this is how I practiced it, this is how I know it, and this is how I feel comfortable with. You see this relationship, you set this equal to there, you solve for dx, you solve for x squared, you solve for u, and then you just algebra. So, hope that helped. See you next time.